Hello, my name is Kończak, and I would like to present the work Failure Recovery from Persistent Memory in Paxos-based state machine replication, done by me and Paweł Wojciechowski at Poznań University of Technology. I will start by introducing Paxos and persistent memory, then I will talk about systems we propose, Paxos and Paxos SM. I will summarize their design and present experimental evaluations. Finally, I will sum up the presentation. State machine replication is an approach for dealing with faults in a distributed system where strong consistency is required. Multiple replicas execute a deterministic state machine and execute the same commands in the same order on every replica. The hard part about building such a system is to order the commands, and for that a consensus protocol such as Paxos is typically used. Those two building blocks must be bound together and interact with clients, and we call code responsible for that the framework. It is important to notice that our framework also guarantees that a client command will be executed at most once. It is important because in a fault-tolerant system, a client can suspect that the replica has crashed and send the request again to another replica. We work in crash recovery model, so we do not consider Byzantine failures. Paxos works so that first a leader is selected, and then the leader proposes commands, and every process agrees on the commands. Obviously, Paxos must tolerate failures, and in order to stay consistent, every process has to keep two promises. First, when a process acknowledges a new leader, it promises to reply only to messages from this leader. Second, when a new leader is selected, the process promises to send all the commands it previously accepted. And this must hold even if a replica crashed and recovered. So to know what the replica did before it crashed, there are several methods. The original Lamport's proposal, which we call full SS, is to write all the data to stable storage. This is pretty easy and works, but it requires synchronously writing the data. And even though there are ways to make the impact of these writes small, we can still see some throughput drop. In order to improve, we can use pure replicas to recover. For instance, there is epoch-SS protocol where we write nothing apart from a single number at start to the stable storage, and when we need to recover, we fetch all the data from pure replicas. Obviously, the pure replicas might not know everything because messages that were sent before crash and will be delivered after recovery may still carry some promises, and we need to handle such messages. However, any algorithm that uses pure replicas to recover has one severe drawback. It restricts the number of processes that can be down at the same time. In any case, when a replica recovers or when it is just late and needs to catch up with the system, it has to get all the commands up until now. Obviously, no replica can have in memory all these commands, so typically a state snapshot is created periodically, and when a replica wants to catch up, it fetches the last snapshot and the commands following it. This is important in terms of performance because creating snapshots periodically decreases throughput. Now, let me go to persistent memory. Persistent memory is basically the same thing as your main memory, but persistent. So from user space, you can access it directly using loads and stores without any page cache in between. It has been for decades as an idea, but as little as last year, it appeared as a product you can buy. Intel Optane DC persistent memory looks just like DRAM. It fits into standard DDR4 slot and can be as large as half a terabyte per single module. It must be supported by your hardware, so this restricts the use of persistent memory modules to very new hardware. In terms of performance, the latency is not that bad, it's 3 times DRAM, and the write bandwidth for a single thread is 0.67 gigabytes per second, and for multiple threads you can get 1/10 of what normal DRAM can offer. And while there are ways to circumvent higher latency, the limited write bandwidth cannot be in any way circumvented. When I talk about persistent memory, it is important to know what is persistent. Normally your data sits in CPU registers, in CPU caches, in write pending queue of the memory controller, and in the memory modules. Not only the data in write pending queue and persistent memory module are persistent. Everything that stays in your caches and is not yet in the memory module or pending queue is lost on a power failure. So you have to flush data out of your caches in order to make sure that they are persistent. However, the CPU can flush any cache line anytime it wants. That means if we have code like this one, where x is written 1, y is written 2, or we want to allocate memory and write the pointer to z, and we want to write some string. Finally, we want to flush the caches to get this all persistent. Then if a power failure occurs before flushing caches, then we can see the following contents of persistent memory when we start the application again. X can still be 0 while y is already 2. This is not consistent with memory ordering of the processor, and it is not consistent with the logic of your application as well. Also, we may allocate the memory but lose a pointer to it, so basically create a persistent memory leak. Also, multiplied variables can be torn between the old and the new value. Such problems are typical for all applications that use persistent memory, and in order to deal with them, a set of libraries, PMDK, has been developed. It aspires to be the standard library for building PM-aware apps, and so far it is the only major one for this. The vital part of the libraries is libpmobj, which provides you with persistent pointers that always point to the same location in the persistent memory, transactions that if a crash occurs within a transaction, then at starting anew will roll back any changes done in the transaction, and memory management that makes it easy to avoid memory leaks. Now, when I have introduced Paxos and persistent memory, let me go to the gist of the presentation. We know that recovery from peers is nice because it has good performance, but it restricts the number of simultaneous crashes. So now, can we retain the performance but allow any number of crashes by using persistent memory? And can we recover faster than any of the algorithms mentioned? There are several ways to use persistent memory in Paxos. The first, most straightforward, is to use persistent memory as Paxos stable storage. This has, however, some drawbacks. Some data will be written twice to DRAM and to PMEM, and on recovery, you will need to read the contents of persistent memory and write it back to DRAM. Our first proposal to make it better Paxos is to use persistent memory as Paxos' main memory, so there will be no data duplication, and Paxos will need no recovery. There will be some overheads introduced by persistent memory and the libraries we use to access persistent memory, and also the state machine will be only in DRAM as in normal Paxos-based state machine replication, so that will need recovery as well. Hence, we propose Paxos SM, where also the state of the state machine will be in DRAM. The good thing about Paxos SM is that the state of the state machine is always persistent, it always survives crashes, so we no longer need to do periodical snapshots, which are a cost in Paxos. And also commands can be erased from the log as soon as they are executed. If we need a snapshot, for instance because a replica asked for a snapshot in order to catch up, we can just send the contents of the persistent memory instead of creating a snapshot manually. To tell you how Paxos and Paxos-SM is designed, I will present the data structures we use. They are divided into Paxos, Replica, and State Machine. To understand the data structures, let me show you how a typical client request is handled. When the client sends a request, first we check whether the command is new or we have executed it. We batch several such commands and we pass them as a batch for Paxos to decide. Paxos forwards the batch to the leader replica, the leader assigns some instance number, votes the batch in that instance, and once it's decided, it is returned to the replica, and the replica puts that into decided instances list. The replica one by one takes the decided instances, unbatches them into single commands, and first checks whether this command has not been executed yet, and passes the command for execution on state machine. Once the state machine executes the command, we record the reply in the list of replies and send the reply to the client. In Paxos, all data of Paxos are stored in persistent memory. The list of decided instances is also stored in persistent memory, but we erase data from this list on a snapshot. And the rest of the data items in Replica are consistent with the snapshot in persistent memory, and the changes since last snapshot are stored in DRAM. In Paxos-SM, all the data, including the state machine, are stored in PMEM. There is one important change here. We no longer need to keep the snapshot in persistent memory because the state machine stays in persistent memory. However, when a replica catches up and fetched a new state of the state machine and installs it, then if a crash occurs, the state of the state machine might be torn between the new and old. In order to solve this problem, we need to store the name of the file we use during catch-up. For further details on design of Paxos and Paxos-SM, please refer to our paper. We wrote prototype implementation of Paxos and Paxos-SM and evaluated them. We used key-value data store as the state machine, which is basically a plain hash map. We implemented it in DRAM for reference Paxos implementation and Paxos, and in PMEM for Paxos-SM. The state machine supports get and put commands, the latter returns old value. We can configure the size of the snapshot by choosing which key range is accessed by the clients. We ran the evaluation on a cluster of machines equipped with Optane. Each replica was on a separate machine and used one NUMA node. The clients were run on separate machines, and all the machines were interconnected with 10 gigabit Ethernet. As a reference implementation and a base to build Paxos and Paxos-SM, we used JPaxos, which supports full SS and epoch SS, and for a fair comparison, we configured JPaxos to use persistent memory as stable storage. To access the persistent memory, we used PMDK libraries, and we wrote that code in C++ because the support for persistent memory in Java is bad. So to use this code, we compile it to a shared library and call it using JNI. We tested each of our systems in 3 memory backends, in RAM backend, where all data is stored to C++ standard containers, and this allows us to see how much performance we lose on moving from Java to C++. Then we tested our systems on emulated persistent memory, which is basically a DRAM range marked as persistent, to see how big is the impact of PMDK libraries. And finally, we ran the systems on real persistent memory. Let me show you how the throughput of the system looks like. Here we see the throughput of the system measured in bytes of client requests per second on varying request size. The top group of the curves is our reference systems and Paxos. The uppermost curve is epoch SS, the bottom blue one is full SS. The yellow line, compared to the green, shows how much Paxos loses on JNI. So we can add this difference to the red line, which is Paxos at Pmem. Even without this correction, Paxos at Pmem is faster than full SS for requests below 3 kilobytes in size, and after this correction it is either faster or on par than full SS for full request size range. The performance of Paxos SM, on the other hand, does not look that good here. But notice that if we run Paxos SM at DRAM using C++ containers, then Paxos SM is the fastest algorithm of all. However, as soon as we enable persistent memory development kit libraries, the performance drops by almost a half. And if we enable persistent memory, it still drops more. Now we identified what is the reason Paxos SM works so slow, and it turned out that the thread that executes requests was to blame. So we profiled that single thread to see why it uses 100% of the CPU all the time. What we saw is that most of the time, 2/3 of the time, it was stuck in PMDK libraries for creating transaction undo logs and committing the transactions and allocating or freeing memory. So this is the work required to bring the state to a consistent one upon starting anew, if a power failure occurred within a transaction. So we can see that persistent memory development kit libraries are not yet suited for writing highly performant code. We tested also the recovery times, and here we ran 3 replicas under heavy load and crashed one of the replicas. After a while we recovered it and measured the time period for 3 stages. First, when the Paxos could order new commands. Second, when Paxos got all the commands ordered so far by the system. And third, when the state machine executed all the commands up to the current one. We can see that Paxos and Paxos SM were the fastest to be able to order new commands, and when it comes to getting all the commands in the memory of the current replica, then epoch SS was the fastest, while among the algorithms that tolerate crash of all replicas at a time, Paxos SM required as little as 2.3 seconds for that. However, to execute all these commands, Paxos SM was the last, because as I have just shown you, what limits performance of Paxos SM most is executing requests. So if we had extra requests to execute, it took extra long time. Now let me sum up the presentation. I have presented Paxos and Paxos SM that enrich Paxos-based state machine replication with persistent memory. Paxos is faster than full SS for small and moderate command sizes and on par otherwise. Paxos SM performance is limited by PMDK libraries, so we observed a very high overhead of PMDK libraries, but we still can say that persistent memory can reduce the time when a replica has only commands after recovering. We still see that epoch SS is the system with highest throughput, but we need to remember that it does not support crash of a majority of replicas, unlike full SS and our systems. We see some potential for future work. We are in fact in progress of modifying Paxos SM to circumvent PMDK as much as possible. And once we complete this, we want to see when the overhead of creating periodical snapshots that is absent in Paxos SM is higher than the overhead Paxos SM has. It would also be nice to measure end-to-end latency of executing the requests, but our implementation is tuned for high throughput rather than latency, so a new implementation would be required for this. Thank you for listening, and please ask the questions during the conference.